Hi, welcome back to another video in the series from the Real World Performance team. Today we're actually going to do a slightly different approach to real world performance. We're actually going to debug and analyze a real production system that was sent to us, and we're going to make reference to the techniques we've described in many of the real world performance videos. And the scenario we're dealing with is we've been given an AWR report by a major online retailer, internet-facing retailer that's got some high-volume transactions coming up, and they're sending it to us 2 months before Thanksgiving and Black Friday. And they're asking, are they going to survive Black Friday? And what we're going to do with my colleague here, Graham, we look at the AWR report. Now, to introduce Graham, it would be not doing him justice to say he knows a little bit about AWR reports. He's actually the father of AWR reports, so he's done a lot of
architect, I prefer, rather than father, but
certainly, you know, we are going to analyze the AWR report in the manner that it was designed to be analyzed and looked at. And what we're going to do is we're going to go through and see what we find and point out things that make us concerned about the performance, the reliability of the system. And would hopefully it's something that you can do on your own systems in the safety of your own home, and figure out whether your systems are vulnerable to various aspects that could bring them down or poor performance.
Right, and the AWR report is quite a big report these days. One of the things that you'll notice through the next few minutes is that we look at a very small percentage of it. Most of the data that's in there is detail that you're not going to use unless something higher up in the hierarchy of the report is really pointing you to it. So there's a couple of key areas that we'll look at, and we'll start off looking at the top of the report. So up at the top we have information that tells us about the system that this is running on. And so, you know, one key thing that we look at up here is how many cores are on the system. And this is telling us that there's 32 cores. It's obviously hyper-threaded because it's saying there's 64 CPUs. Right, so we've got 32 cores on this system. The next section is telling us that at the start of this period, which is just over 100 minutes, we had 3,300 sessions running against the database. Now, if you've got 32 cores, you're not going to be able to successfully run 3,300 sessions. Right? If you come back to the computer science of it, you cannot run 100 sessions on one core. Right? They just can't do it. So first red flag there is that's a very high session count. And then if we look at the end snap, it had actually grown from 3,300 to 4,600. So we started with a very high session count, and now it's grown dynamically over time.
So, you know, two red flags immediately are coming out of that. One, it looks like we're way oversubscribed and overprocessed. And the second one is we have a dynamic connection pool. We've covered in numerous demos what happens with a dynamic connection pool, so that certainly the data here is starting to indicate, one, too many processes, and two, a dynamic connection pool. Perhaps we should just look at the logons per second and do some mental arithmetic with that.
Yeah, so if we scroll down to the load profile, we have logons per second of 10.5. Right, now that works out at
100 minutes.
Yeah. Per the 100 minutes, that's about 60,000 logons. So that's obviously not DBAs logging into the system. You know, often when we highlight a logons per second, and normally if it's one logon per second, customers will say, oh yeah, it's the DBAs logging on and checking space or something. If it's 10.5 logons per second, it's obviously not that. And this is the average over a 100-minute period.
Yeah, that's think about that, 60 seconds, 10 of these seconds, that's 600 logons a minute. You don't even do rocket science how many things there are. That's not someone just being curious about checking space. Right. There is an architectural problem with the middleware at this point in time.
Right, and that number of logons per second, logons don't come for free. They're very expensive in terms of the resources that are needed both for logging on, and actually logging off is more expensive than logging on. Folks don't often think about the log off side of it, but you've got to release all of the areas that you had in the shared pool. That can get very expensive.
And we actually think this is actually a lot worse than this, because this is 100 minutes and this is the average. This is probably a dumbed down result by virtue of the averaging process.
Right, yeah, one of the problems that we have when we're looking at AWRs, especially longer period AWRs like this, is that unless the workload is completely stable over that time period, then any peaks in problems will get averaged down. So it may well be that this 10.5 average logons per second, there were times when we were doing over 100 logons per second.
And remember when we were having the demo with the gaming application, we peaked out and we couldn't get beyond about 300 logons per second, and that was the upper limit for the application.
Right.
That was it, done, finished.
Yeah, so it's very easy to have a period of time when you're just completely maxing the system out on, or you're serializing behind logons. In your AWR, over a time period like this, it's getting averaged down. The other reason why that's a concern, why dynamic connection pools are a concern, if we look up, DB time, we've got about 260 active sessions on average over the time period. We've got 32 cores, and there's 39 sessions on CPU over that time. Now, how much of that time is being spent in logging on and logging off? We're short on resource, so spending a lot of that time logging on and logging off isn't really helping our throughput.
Yeah, and the other thing is you see 32 CPU seconds per second on 32 cores. Well, we're going to have a lot of that accounted through by getting virtue of the hyperthreading, but you can see we're fairly well oversubscribed. And what did we learn from the demos? When you're oversubscribed, the response time becomes volatile, it becomes variable, it becomes unpredictable. So at this point of time, we have a system that's been measuring when it's in an undeterministic, unpredictable state. Not the sort of thing you want to have on a flagship website at Thanksgiving.
Right, yeah. Okay, so just very quickly, the other things here, no particular problems in terms of number of parsers, nearly 40,000 per second is kind of getting up there. Hard parsers of 0.1, that's obviously fine. Transactions per second is 1,300. Now for a stress test of a major retail system, that seems kind of low. I would expect to be able to manage many more transactions per second than that.
Notice we're just shy of 60,000 transactions per SQL statements per second. Right. So you can see the number of SQL statements per transaction, but again, for a system that's got 32 cores, this is not a dramatically high number. So there's two questions: is the connection architecture dumbing down the performance like we saw in the demos, or is perhaps some of the SQL fairly suboptimal and actually could be better designed SQL or better optimized?
Yeah, I'm sure we'll come back to the SQL in a bit.
It always comes back to SQL in the end, so let's be...
Okay, so now we looked at the top of...
Do you want to have a look at the cursors at the top?
Oh,
yeah,
right.
Look and do a sort of leakage check.
Yeah, okay, so the other thing that we notice up here, as well as increasing from 3,300 to 4,600 sessions, the cursors per session has gone up from 8 to 26. Now, if you think about that, this is the same application that's been running throughout this 100 minutes, because it's a stress test of that same app. So if the number of cursors per session is changing, that means that we are leaking cursors. Right? The only way that you can start using more cursors over time is if your application is leaking cursors. So again, that's a red flag for us.
Yeah, so but maybe if we actually look at the bottom for the initialization and init.error parameter settings, let's go and have a look for OpenCursors and see what that's set at.
Right, so OpenCursors here is 2000. Again, OpenCursors is often misunderstood and people think that it's a per system limit, database-wide limit. It's actually a per session limit. So this is saying that an individual session running against the database can concurrently have 2,000 cursors open and returning data or inserting. And
one clever programmer, isn't it?
you've got to be pretty smart to be able to remember the state of all 2,000 cursors to do that. Now, in practice, what happens with these things is that OpenCursors get set to a high value because at some stage they've run out of cursors. And the DBA has been told, oh, the application's hitting the error saying max OpenCursors exceeded. So the DBA will bump it up so that it gets it off his list of things to do, right? It just goes away. Well, in fact, it's not going away. All that's happening is he's just masking the problem, and it will come back at some later stage, right? So
basically allocating memory and resources that aren't needed, that can never ever be programmatically reached because they've been programmatically leaked. So you're wasting resources, and it's just like a time bomb. Just by setting it off for a bigger number, it means it's going to blow at some point. You just don't know when it's going to blow.
Right. Yeah. So as well as upping the limit, what we like DBAs to do is actually look at the system and look at $, OpenCursors for one of the sessions that's having the problem. You'll probably see that there are many copies of several of the cursors, and that's how you identify cursor leaking. And once you're looking in the right place, it's real easy to identify, real easy to bug.
This is where just good development practice comes in. If we can identify the SQL statement that is being leaked, and even better if they are attaching module information associated with the SQL statements or good comments on the SQL statement, basically it can help the programmer trace back to the SQL statement that is leaking a cursor, and then we may be able to find out where the logic problem is, where they're perhaps throwing an exception without tidying up behind themselves and things like that, as to why the cursor leak took place in the first place. So, it's looking like we've got here session leaking, we've got cursor leaking. There's one other thing we should look for, which is the last type of leakage, which can bring a system to its halt, and that's lock leaking.
Yeah, so you mentioned session leaking. Having sessions set to 8,300 here is another indication that might be a problem. So for lock leaking, let's go back and find our...
Let's see if we're spending any time in NQs, really.
Yeah, let's get back to our top 10. Oh, there we go. Our timed events now. Okay, so our top wait event is actually a library cache mutexx. Now, again, I could see from what we've already looked at, two possible causes of that. One is the logons per second, which mean that we're actually having to parse statements each time we log on. The second one is that we're CPU bound on this system, and on a system that is CPU bound, latches and mutexes will tend to come up as the top events because in normal operation they're held for a very short time and then released again. If you're CPU bound, that very short time gets increased dramatically by the time that your process is spending in the run queue.
It's quite ridiculous in this case. You hear average time, and I know we don't like to talk about averages, but even an average of 7 milliseconds.
Waiting for a mutex, which should be microseconds.
Yeah, it should be in microseconds. That's the speed of an I/O. We're exchanging control of a piece of memory. This is something that's not right.
Yeah. And you can see there's also another latch down here as well, which that one's got some nearly 2 seconds average wait for that one. So, but then getting back to the locking issues, our second highest wait event is TX row lock contention. So waiting for row locks, and we've got 250,000 of those over this 100-minute period, with an average time of a little bit over a second. So we're spending a lot of time waiting for locks. Now, of course, that then feeds back into the application server. Because our sessions are waiting for locks, the session is active as far as the application server is concerned for longer, and therefore the application server ends up creating more sessions so that it's got a free session to work with. And it all just spirals down from there. So that is probably at least part of the reason why we've got our increase in the number of sessions as well.
I've heard from this site that they have scripts that go off and kill lock holders that have been holding locks for a while. So, we should be suspicious of all three types of leakage. Cursor leakage, session leakage, and lock leakage. There's enough evidence there to ask those hard questions.
Right. Yeah, and well, the fact that they have kill scripts that run on a regular basis is in itself.
And then the thing that we always hate to talk about is that if they've got kill scripts that are killing off lock holders, are they logically corrupting the database at the same time? The problem is nobody will ever know until it's too late, and it's rather unfortunate. And so there's that aspect of it.
Right, and so, well, we have lock contention, so if we look down at the SQL, then we should be able to identify fairly easily which SQL statements are responsible for most of the locking, because they'll be the ones where we're spending most of the time. And so if we look at the first SQL statement here, which is responsible for 12% of the overall load of the system, and this says it's a select statement here. So, well, you wouldn't expect a select statement.
Yeah, let's just look at those numbers. They're 12% of the load, but it's barely even 0.6% of the CPU burnt on the system.
Right.
So it's actually a tiny resource consumer, but in terms of wall clock time, it's taking a long time.
Yeah, and even if you include the I/O times in this, it's still just a little bit over 3% of the execution time of this SQL statement is spent on CPU and I/O, and the rest of it is likely spent waiting for locks. Okay, so let's go look and see what this SQL statement is. And here's our SQL statement. And yes, it is a select, but it's a select for update. So that's why we were seeing a select there as being responsible for a lot of time, which is probably down to the locking that we were seeing. Right, so select for update is going to try and take out the locks. If it can't get the locks, it's going to have to wait for them.
Okay, so you can see we've probably got a locking problem. But I saw something as you were scrolling through the SQL statements just then. I saw some statements.
Yes.
With some mighty long in lists and some system-generated bind variables.
Right. So, we didn't look at it in the init.org when we looked down at the init.ora, but the fact that these bind variables are all sys_b and then a number, this system must be running with cursor sharing equals force, because that's the way that system-generated binds will appear.
Or a session with its sec.
Or a session with it, yeah.
So, as you can see, it's
a long in list.
A long dynamic in list. So, basically, someone wrote a program to dynamically create an in list, probably with a variable number of elements in the in list, put them in as literals, and now we've converted them to bind variables, and so we have to parse that statement and then bind in all the bind variables. And it makes me wonder, shouldn't have that been a subquery feeding into a join? This is just SQL efficiency, but at this point in time, we're not too worried about these things from a performance perspective, because we found the big hitters up front, which was the dynamic connection pools and potential resource leakages. But the thing is, we do get nervous when we start seeing cursor sharing equals force and these sort of things.
Yeah, because it has all sorts of knock-on effects. So if we look down here, this next statement actually is a to-date statement, and that second bind there will have been a date format. Now, I'm sure that the developer, when he wrote this, put in a literal of a date format, which has been converted into a system-generated bind.
It would have been a date in a date format, and then the format mask.
Right. Yeah,
and now it's all being bound in as bind variables, and any formatting would have been lost associated with that.
Yeah, and in this case, obviously, that wasn't affecting the application, but in some cases, just turning cursor sharing equals to force. That sort of substitution, which is not necessarily what the developer was expecting to happen, can cause errors anyway.
The other thing that makes us, of course, a bit nervous about people basically saying cursor sharing to force, because they have either a programmatic screen scraping application or they're dynamically generating SQL statements. It makes them awfully vulnerable to SQL injection. And with that in mind, we just get nervous, and all we can do is red flag this and say, potentially, you're open to SQL injection. And again, 2 months before Thanksgiving, you don't want to hear that.
Right.
But the reality is, potentially, this system may have some security flaws. So, just to wrap up what we've done, we've basically had a look at we've been able to reverse engineer a lot of facts about the connection architecture, probably about how much QA went into the programming, looking for resource leakages, and we've identified a potential security flaw.
Mm-hmm.
Okay.
And we've done that by looking at a very tiny proportion of the AWR report. We haven't gone into looking at all of the sysstats. We haven't gone into all the disk IOs. Wasn't relevant in this case.
So, Graham, 2 months to Thanksgiving, should these guys be checking up on their resume?
I would hope so. That's what I'd be doing if I was there.
Okay, so again, hopefully everybody, when you've seen this video, it's given you some ideas as to what to check for, the sequence and what to check for, and start critiquing your own systems at home. Don't wait to figure it out. Don't wait for it to blow up. You can start doing this proactively yourself. Use it in conjunction with the real-world videos. In many cases, these videos get sent to educate other people about the nature of the problem, because we have demos demonstrating the race conditions. So, perhaps this conversation should be happening over cups of coffee all around the world, and people attempting to make their systems more robust, faster, and stable. And at that point, Graham, thank you very much.
Okay, thank you.